All right, so it is week 14. We are on, I guess in some ways, maybe my favorite chapter of the whole book, because what the authors do here is bring together all the renewable energy technologies that we've been discussing up to this point into integration. And so a lot of times, I'm asked, so what's the best energy to use? I go, well, there's no one best. It depends on where you are, what the availability is. Since I had this talk up previously, I wanted to show once again this slide. So if you go out to the solutionsproject.org, and I know I've shown this briefly, but they sort of list what the renewable energy profile is going to look like, at least in their vision, for each of the 50 states. Like if you're like, the United States is going to invest in clean power. What's that mean? Well, it means all of these different types of power, 3 types of PV. You got wave, you got solar thermal, you've got concentrated solar for electricity, geothermal, offshore wind, onshore wind, hydroelectric, etc., tidal turbines. Everything we've been discussing up to this point, they're all going to have to be integrated on the big scale. It's going to be windy somewhere, sunny somewhere else, et cetera, and each state sort of has its optimal solution. So that's really what this integration chapter is about. So let's go to courses, hit 102, and let's look at our figures. Integration. I also, just for the record, I want to tell the world on YouTube, here we are, live stream, really how great this Open University Press has been to work with out of England. I've got great representatives. So again, that's our textbook, Godfrey Boyle. It's Oxford, out of Oxford, the Open University out of Oxford, and so they just share these figures with me from the chapters, and they've been a great resource for delivering this course. Okay, so very first figure in chapter 10, integrating renewable energy. I'll just read the first paragraph. It says, renewable energy already makes a large contribution to world primary energy needs. It says in 2009, it amounted to about 13%, and that was all the way back in figure 1.2. It said between 2005 and 2010, world fossil fuel consumption increased slowly, while total nuclear electricity consumption has not grown. It says, however, various renewable energy technologies have seen high growth rates. See figure 10.1. So fossil fuel consumption did go up, and that's the annual growth rate. And remember, that's 2% per year, and kind of think back to what we did in finances with our interest rates and all that. Nuclear, not so much. Solar water heating capacity, it's growing by 16% per year. So if you're thinking about, hey, where do I invest some money, anything is returning that. Concentrating solar, 25, solar PV, 50% growth per year. I mean, it's going to go berserk here pretty soon. Ethanol production, biodiesel production, hydroelectric. I think hydroelectric is fairly mature. You might see some micro hydro coming online. Wind going gangbusters, geothermal capacity is growing, and it's going to explode. It's going to go off the charts here pretty soon as well. So, okay, so these renewable energy growth rates seem likely to continue, spurred on by concerns about climate change, limited fossil fuel reserves, and the external costs. So chapter 2.9, we reviewed each of the renewable energy sources in turn, and then the big question says, can renewables deliver our energy not only in significant amounts and at an acceptable price? I had that discussion already this morning with Patrick Barkey and Bob Seidenschwartz. I called in to the show Talkback and said that we could save a lot of money in forest fighting if we went out and harvested the fuel now, and I think we would see much better tourism in Montana in the summer if the skies weren't so smoky. So we clean up the air, clean up the coal, put the carbon back in the ground. I mean, and that's what integration is about, and that's what this chapter is about. The right time and the right place. What are the factors that make it difficult? A lot of times it's just getting access to the national forests themselves. You've got so many people saying keep the loggers out of the forest, what have you. And so the barriers at this point are more or less social or political. The technological barriers are if not gone, quickly disappearing. Okay. It does say in section 10.4, we just discussed the available resource or potential for each renewable and how it might have practical or economic constraints to see how large they can actually become. And then we've got financial costs, some methods that the government and non-government organizations have been promoting it, and then some different energy scenarios. Okay, so 10.2 says the existing UK energy systems, liquid fuels, 43%, almost entirely from oil, and then its derivatives, gasoline, diesel, kerosene, and a little bit of ethanol and biodiesel coming online. Gaseous, 34%, and then solid fuels, and this is atypical. Only 2% of England's or Great Britain or the UK, the United Kingdom's energy comes from solid fuels. They burned through all their coal a long time ago. Electricity, some from fossil fuel, other from nuclear, and then heat. Says in 2010, this is actually delivering heat. 2% of heat is actually delivered, deployed by a limited extent, heat energy through buildings directly in the form of hot water or steam, district heating. And I'm really looking forward to doing some district heating in Missoula. I think it would go over great because the hot summers and the cold winters, you bank the hot in the winter, you bank bank the hot in the summer for use in the winter, bank the cold in the winter for use in the summer. And I've got a giant, well not giant, but I've got an ice monolith standing in my front yard right now because it was so cold I was just making ice. And if I were to be taking that ice underground under my shed, it would feel pretty good there in the summer. And no reason not to do it. So, yeah. Okay, but it's just barely happening. Okay, so distribution. It says it's worth dwelling a little bit on the changing nature of our energy distribution. Here's a shot of what it looks like, or it can look like. It says most of the UK's energy demand occurs within the relatively small areas of major cities. Many of these are built in sheltered inland valleys deliberately to avoid the worst excesses of wind and wave energy. And that's a little bit like Missoula too. We're in a sheltered valley here to avoid the excesses of wind, not waves so much. Well, unless Lake Missoula comes back, but might be a while. Many large industrial towns grew up and around their fuel supplies, coal or wood. Some faded into obscurity when their fuel ran out. Others survived by importing fossil fuels. All right. So if we look at figure 10.2, and it says looking beyond the UK, there's an impressive Europe-wide system of pipelines for gas distribution. If I understand correctly, that's some of the reason for the conflicts between Russia and the Ukraine. Is over energy distribution because Russia, I think, can turn off the tap at will and people die without appropriate access to energy. It says, stretching from the gas fields in Algeria, south to Norway in the north, from Siberia and the Caspian Sea to the east of the Republic of Ireland. So this is what the pipeline looks like close up. This is what the compressed natural gas or liquid natural gas tankers look like. And this is what our global civilization is starting to become. Now, right now, this is being used to pump natural gas from the Earth's natural resources. I'm looking towards the future and thinking that ultimately this is going to be for sequestering gas and sequestering waste. One of the things I would like to do at 8 Columbine is just to take down the stacks, pump all of that greenhouse gas into the sewer systems, cap the sewer systems, and the sewer systems are they either go uphill or downhill depending on which direction you're moving at a very slight gradient. But if you've got all that gas stored, this could become your CO2, methane, greenhouse gas sequestration system. Right now, it's sort of flowing up out of the earth. Once we get the solar, the wind, the wave, et cetera, online, we can then take this to pump and process and concentrate the greenhouse gases rather than just allowing them to diffuse into the atmosphere. So right now, it's a one-way street towards us. In the future, I think it's going to be a, multi-directional interchange once we get our Greenhouse Gas Act together. Okay. We mentioned district heating. I know these guys are geeked about it. So am I. So here you see a heavily insulated tube. If you ever go to the rec center on main campus, you'll see tubes like this. They're carrying steam to different parts of the campus. This is much more aggressive, where you're actually conveying it between buildings. And if we had our act together a little bit better, and I think once we do start to move away from these large coal-fired power plants, we might start to see smaller cogen plants. They're going to make heat. Where do you want it? Well, we pay for heat all the time, right? When you pay your natural gas bill, you're paying for heat. Or even your water bill, you're paying for hot water so you can take a shower and cook and clean and all that stuff. Okay, the next table is not, I don't have a figure for it, but I'm just going to read from table 10.1. It says specific CO2 emission factors for UK electricity in 2010 and an approximate external cost of associated carbon emissions. I asked this question directly. So when I got on the phone with Patrick Barkey this morning, I was trying to inform the public that I think we do have a solution for carbon pollution in Montana and for beetle kill sequestration in Montana. And then the host, I think it was John King, said, "So Brad, do you have a question?" Because Bob said, Leighton, take all the time you want. Let's just hear what you got. There were maybe 10 minutes left in the show, and so I yacked for a minute or two, but then he said, "Do you have a question?" I said, "Well, yeah, I do, in fact." And my question for Patrick Barkey is what does he see the cost of carbon being in the future? Because I've heard that Northwestern Energy is going to work in a carbon penalty price into its electricity generation. And why would you do that? Well, so that you can actually pay for some of the technologies that need to happen for sequestration and development of renewables. He did not really know the answer because he seemed to think that if that happens, Montana is going to be one of the last states to comply, which is unfortunate because I think we have such energy resources here, we could really be ahead of the curve and progressive and like I said, I said let's just keep that very valuable coal in the ground for future generations. We love it. Let's save it. Let's preserve it. Okay, but the numbers we're looking at here, external cost at an assumed price of 40 pounds per ton. So last week we were looking at 30 to 60 pounds per ton. That's the penalty cost that we've been looking at. What does that turn out to be? Well, it turns out to be 1 to 3 cents per kilowatt hour. So your cost of your electricity just went up by 10%. So what that's doing is taking the externalities that we've been talking about earlier and turning them into an internal cost. So you're building that cost of carbon into the economic model. Okay. Okay, so here's UK electricity generation, mostly from gas, some still from oil, or coal, imported coal, remarkably a little bit from oil. I don't know if that's waste oil. I would be surprised if that was primary oil. Wind, fairly large. Nuclear, pretty impressive at 15%. It's kind of weird, but that 3.4%, that's solar's in there somewhere. I mean, solar's got to be there, but it's still pretty modest, but growing. Okay, and then what happens then? So this is specific greenhouse gas emissions for several electricity generations. So if you are burning lignite, you have about a kilogram of CO2 per kilowatt hour. Kilogram of CO2. Make 1,000 of those, you've got a megawatt hour. 1,000 of those, and you've got a ton of CO2. You add up the whole human population, and we're looking at 37 to 40 billion tons of CO2. This is all with conventional. If you do your carbon sequestration, it's a lot less, obviously. There's some CO2 associated with hydro, and it's not 100% clear to me where that is coming from. I don't know if that is from the in the development. So when you actually go and build your dam, there's a little bit of CO2 there. That's kind of the average over the lifespan of the dam. I don't know if it's a result of deforestation that it might occur as the result of building a dam. I'm just surprised it's that high. Some of these others, we mentioned that when you dig a geothermal well, a lot of times greenhouse gases will come up with it. When they say CO2 equivalent, so 20 grams of CO2 is the same as 1 gram of methane in terms of a greenhouse gas. So when they say CO2e, it doesn't just mean that there's CO2 coming off. It means that each one of these technologies has that equivalent of a gram of CO2 in the atmosphere. So it could even be there's only no CO2 associated with hydro, beyond what's the concrete manufacturing and all that, but it's just the equivalent warming. But bottom line is all the renewables do not have that CO2 release. Okay, so the next section, 10.4, says how much renewable energy is available. And we've done this already. We've shown like that. 130,000 years worth of geothermal energy just in the continental U.S. if we tap it all from 7 kilometers down. And then there's obviously a difference among available, technical, practical, and economic. So even on that little PowerPoint I was showing you, or the YouTube video rather. I won't bring it back up. Even that YouTube video I was showing you with 8 Columbine and wanting to put solar thermal on the side. There's a lot of sunlight that hits the house, right? So there it is hitting the house. Now technically, how much can I grab? Well, do I want to go in and cover the whole house? Yeah, maybe not. And there might be places where you still have to have screws and fasteners and edges, so that reduces, so that the technical is always going to be less than the available, just because of how diligent you are in putting up your renewable tech. Practical, then it's like, well, I couldn't quite get on the ladder, or the tree was in the way, or just whatever. There's a lot of other just practical things, or I couldn't get a board that was 5 feet long. I could only use a 4 foot long. Just regular everyday hurdles. And then the economics. Well, somebody's got to pay for it, and if in the long run it doesn't pay back, then the people with the money aren't going to put the money in now, so they can get their money back later. And so a lot of it hinges on that cost of carbon. If carbon ends up having a cost, that money's got to go somewhere. Where's it going to go? It's going to go right here, and then all these other things will rise along with it. So these bars are highly interrelated. The available, not so much, but more economic will drive up the practical and the technical as well. Okay. Now here's your price per kilowatt hour. I'm just going to hop ahead a little bit, then we'll go back. So we're on page 474. This is figure 10.9, and we're looking at pence per kilowatt hour. So in Montana, we're used to paying about 10 cents a kilowatt hour. That's something like 6 pence or so. So here's about what we pay on average for electricity in Montana. It is less than, well, it's way less than the rest of the world, just because we got so much energy here. Okay, and now the reason, at least at the time of writing, that these other conventional coal, gas turbine with CCS, coal, etc., were sort of winning is because they're cheaper on a per kilowatt basis than solar, which is right there. Biomass, fairly competitive. Hydro, not too bad either. You look at the tidal barrages that we're all excited about, like, whoa, that's pretty spendy. Same thing with the floating wave, floating wave technologies. Great, but there's a lot of upfront cost, and you might not get your bang for your buck. Another thing to note is that there are no fuel costs in these so-called green or renewable energy technologies. Okay, and then let's do look at table 10.2. And it says global technical potential for some electricity generating renewables. Hydroelectric is 14,000 terawatt hours per year. Let's see what let's turn our exajoules into terawatt hours. Let's just do that with Microsoft Excel really quick, because I want to see what fraction each one of these is good for. So let's do this. Exajoules per year. So we're looking at 500, right? And so let's turn that into joules per year. It equals that number times 1E18. So 5 times 10 to the 20th joules. And then let's do megajoules too. Equals that number divided by 1E6, so divided by 1,000,000, so there's that many megajoules. And then a kilowatt hour, there are 3.6 megajoules in a kilowatt hour. 3.6 megajoules in a kilowatt hour. So one kilowatt hour is 3.6 megajoules. So this number has to go down, equals this number divided by 3.6. Control 1. You know, here's what I'm gonna. Well, I'll change all these numbers in a second, and then let's just do megawatt hours equals that divided by 1,000, and now we'll do gigawatt hours per year equals that divided by 1,000, and then we'll do terawatt hours per year equals that divided by 1,000. Okay, now I'm going to take all these numbers, do a control 1, and hit it with the custom, and I like to use the engineering notation on this. Here we go. This is the engineering notation right here. It's got three, it'll have 1, 2, or 3 digits to the left of the decimal point, and all of the exponents are some power of 3. So that makes it sort of easy for mega, et cetera, et cetera. Okay, and I'm actually going to take this guy. Let's take them all, and we can paste them over here. Oh, no. It added 1 to everything, didn't it? That's pretty funny. Let's see if this works. Okay, now I can take these and turn them into another format. This is just kind of fun to do in Microsoft Excel, depending on what way you like to look at numbers. Okay, so humanity consumes, man, is that right? Okay, 138,000 terawatt hours per year. That's more than I would have thought. Let's just double check. So 500 exajoules, that's 500 times 10 to the 18th joules. That goes down by a factor of 6. This is the one I'm always worried about. Kilowatt hours to megajoules. I'm just going to triple check myself. Sometimes I get division dyslexia. 1 kilowatt hour to megajoules. 1 kilowatt hour is 3.6 megajoules. So this number has to be smaller than that one, and it is, by a factor of 3.6. So I did it right. And then went from kilo to mega, we went down by 3 orders of magnitude. We went from mega to giga, another 3. Giga to tera by another 3. Okay, so that's still, I gotta go one more. Equals that divided by 1,000. Oops, 1,000. Copy, paste, control 1, number, no, okay. So, humanity consumes the equivalent of 139 petawatt hours of energy per year. Now, let's look again at table 10.1, and the ranges that I'm seeing for hydroelectric, that's 14,000 terawatt hours. So hydroelectric could potentially give us 10% of our current global, 10%. Wind power, well, 24,000 to 160,000. That's kind of good news. If we used all the technical potential of wind, we'd be there. Ocean energy, 2,090, that's a pretty good chunk too. Geothermal, we're knocking on 310, so that's also pretty good news. But it's almost at parity. I mean, it's almost equal. So, yeah, and that gets back to the fact that our energy per capita on a global basis is also diminished. And then table 10.3 shows a few things in the UK. You can see there's a lot of offshore wind. That's their major contributor. Okay, so I'll take a break there, and then we'll get back into 10.5.